Okay. Well, I'm really glad to be here and to celebrate Carl and Dick really for having set the pathway to a lot of the almost next generations. I don't know whether I'm the next generation of their own, but I'm sort of in between. But anyway, I have been strongly influenced by them. And so I'm really happy to be here. What I'm not so happy about is the fact that I won't be able to talk about everything I wanted to talk about. So I'll just talk mostly about the magnetic field in the process of molecular cloud assembly. And so this is a concept that will be underlying my talk throughout. And to get the point of this idea of how a cloud gets assembled, we can go to back to the basics and just remember that the continuity equation of fluid dynamics tells you, of gas dynamics, tells you that the total derivative of the density equals minus the density times the divergence of the velocity. And minus a divergence is a convergence. So every time you want to form a cloud, you need to have converging flows. So that means that this is in part because there has been a sort of confusion in the literature where the term converging flows has been used mostly in the sense of local turbulent motions. But no, every time you want to create a density enhancement, you must have a converging flow. And that is regardless of what is the driver. And in particular, one of my favorite drivers for this is the potential well of the stellar spiral arm. And I'll get back to that. So converging flows are necessary, absolutely necessary for forming density fluctuations. So, but in the case of the atomic medium, the converging flows are aided by the thermal instability, which has been discussed already quite extensively, by which the compression triggers a transition from the warm neutral medium to the cold neutral medium. And in a paper in 2006, we pointed out that that implies that when you have this, the gas flow going into the clouds, they undergo the phase transition at a condensation front through which the material is flowing. So what this means is that the boundaries of clouds are not rigid walls. They are actually condensation fronts through which the gas is flowing into the clouds. And this means, one, that clouds start out as probably thin sheets, like Carl observed at the turn of the century, and then they grow both in mass and size by accretion from the diffuse medium. So that's the essential cloud assembly process. And so what is the role of the magnetic field in this process? Well, for that, I would like to go back and talk a little bit about some work that we did on nonlinear MHD waves with Thierry Passot about some 13 years ago, where we looked at the dependence of the magnetic pressure, that is essentially B squared, the square of the magnetic field strength, as a function of the density. That's a nice feature of these nonlinear simple waves, that you can isolate one variable in terms of any other. And we found the dependence for the different modes of the MHD waves. And so what we found is that for the fast wave, the magnetic pressure scales like the square of the density. For the slow wave, you have a very non-intuitive behavior, which is that the magnetic field strength relates inversely with the density, but with this constant in front of it. So I'll show you what it looks like in a log-log diagram in a second. And then for the circularly polarized Alfvén wave, you get a polytropic-like dependence that depends on the strength of your turbulence, on the Alfvénic Mach number. And so in that same paper, we were able to produce some simplified numerical simulations in 1 + 2/3 dimensions, where we were able to, by adjusting the geometry of the adjusting the direction of the magnetic field and the propagation of the waves, we were able to single out any of the modes. And so this is a simulation in which we singled out this low mode, and indeed, this is what this dependence looks like. This dependence looks like in a log-log plot. So at low values of the density, the magnetic pressure goes to constant, and at high values of the density, it drops. And you see that for some above some densities, this mode cannot exist. Therefore, this low mode exists and is nearly constant at low densities, and then it drops off and dies at high densities. On the contrary, the fast mode just goes like the square of the density, so the pressure of that mode goes like the square of the density, so it's just like like this, which means that at low densities the slow mode dominates, and at high densities the fast mode and perhaps the alpha-in mode dominates. Now, I would like to go back here and mention the fact that a typical example of what the slow wave is precisely motion along the field lines. So that's why you can get a field that is nearly independent of the density at some point. Well, so when you put all modes together, you get this kind of shape of distribution of the pressure, of the magnetic pressure as a function of density. This is like a two-dimensional histogram, and you see that it's relatively flat at low densities, and then it increases at some power of the density at high densities, depending on the alpha-in Mach number. Well, this is pretty reminiscent of what Dick Crutcher has told us, that the magnetic field looks like as a function of density in the ISM. This being mostly densities corresponding to the atomic medium, and these corresponding to the molecular medium. So in this scenario, the cloud assembly can be interpreted as a slow mode of the MHD waves, of the nonlinear MHD waves, because cloud assembly can occur along magnetic field lines without the magnetic field being perturbed at all by the motions. Then, of course, the motions must act along the magnetic field lines, but this is what the slow wave is. And in this case, you can think about the mass-to-flux ratio of the material that you have collected. And as you collect more and more material, your mass-to-flux ratio increases. And we know that there is a critical value of the column density as a function of the magnetic field strength, above which the medium becomes magnetically supercritical. And this expression implies an accumulation length for typical values of the magnetic field and the density of about 500 parsecs in the ISM. So that means that if you collect material from about 500 parsecs around into a cloud, you will have formed a magnetically supercritical cloud. And it's interesting that this critical density, column density, is actually very similar as what we were hearing earlier on today by Tom. Is similar also to the column density at which the gas becomes molecular, and also to the column density at which the gas becomes self-gravitating. So, in other words, Hartman et al. 2001 pointed out that when you're forming a dense cloud, this cloud is going to become roughly, it's going to become magnetically supercritical, molecular, and self-gravitating at roughly the same column density. And that's how we interpret the plot, this density, dependence of the magnetic field and the density. And before Alex jumps at me and tells me that this is too long a length to collect the material from, please remember that a spiral arm, which, like I said, is my favorite collecting mechanism, is about 1 kiloparsec wide, so there's plenty of room to collect material. So this is the picture of what is the role of the magnetic field in the assembly of the clouds. In the low column density or low density regions, basically what you have is the accumulation stage occurring that is transforming the WM into the CNM. And as you become dense enough for the gas to become magnetically supercritical, molecular, and self-gravitating, then you begin contracting and begin to go up. And clouds evolve in this direction. So that's a picture that we have been promoting for the last few years. So, and I would like to emphasize that this is a purely ideal, non-dissipative, non-diffusive MHD process. And this would be in addition to whatever dissipative or diffusive processes may be occurring, like what Ellen and Alex have been promoting on their own. So that's one part of it. The other part is a much more recent result. In fact, it's, the paper is about to be submitted. And that's a result that was quite surprising to us, In fact, this is not something we were expecting. We have been doing numerical simulations of the assembly of clouds in the presence of the magnetic field. And what we found, to our surprise, is that the presence of the magnetic field tends to suppress the generation of turbulence in the clouds. As we know, there have been many papers that have written about the generation of turbulence in the layer that is produced by the convergence of gas streams, of low-density gas streams. And it is known that this turbulence is essentially produced by a combination of instabilities, perhaps the most important of which is the nonlinear thin shell instability that Ethan Vishniak worked out in the isothermal case in 20 years ago. So how does what happens? What do simulations with different degrees of magnetic field strengths look like? Here's a set of 4 simulations with no magnetic field. So these are simulations in which the magnetic field on the top row is perpendicular to the screen, on the bottom row is horizontal. And so here you see the formation of the clouds face on, and here you see it edge on. The flows are coming in perpendicular to the screen on the top and are coming in horizontally. So the flow is along the field. And what you see is that the stronger the magnetic field, the less turbulent the cloud is and the more compact it is. So why? This is our interpretation of this, is that the nonlinear thin shell instability generates turbulence because it acts by amplifying bending perturbations on the layer boundary. So as the flows come in, they push the material on the boundary and accumulate it at the nodes of this thing. And so it creates clumps at the nodes and generates transverse motions. So now if you have a magnetic field that is running more or less perpendicular to the boundary, then that tends to suppress motion along along the boundary. And so what we did is we measured, for example, the velocity dispersion in the perpendicular direction in these simulations. And you see that the largest velocity dispersion, perpendicular velocity dispersion, occurs indeed in the case with no magnetic field, and then the magnetic cases drop. And this is the longitudinal velocity dispersion, which is also depressed in the case with magnetic fields because you don't have this engine that pushes the gas along the lines. And this has implications for the star formation because then the star formation has to wait in the non-magnetic case until the turbulence in the whole cloud is dissipated, and then the cloud can begin to collapse. So this is a picture like what we normally associate with cloud cores, but here it is occurring more at the scale of GMCs. And so with that, oops, wrong button as usual. Yeah, so basically, but one thing is that the star formation rate actually picks up faster once the collapse has started, because now the absence of the magnetic field allows the collapse to occur more rapidly. So that's the part I'll just have to refer you to the paper because I have no time to talk about it. And here are my conclusions. I can leave these two, which are the ones I just talked about. And if I had had time to talk about that, I would have told you that our synthetic observations tend to suggest that the fraction of CO-free gas and CO observable gas vary during the evolution of the cloud, and that the CO gas tends to appear by the time the density PDF is becoming a power law. Thank you.
All right, we have time for questions.
Susan. Thanks. Do you think it's a problem for the slow mode accretion or accumulation picture that in the low density gas, the structures are so consistently parallel to the orientation of the magnetic field?
That's a good question. Here we're assuming, okay, so I had never stopped to think about it. So it's a good question, but probably not, because as long as you don't have a real collapse going on and a real phase transition, then the motions must be confined be along the magnetic field lines. That would be the slow mode. And then you would have whatever perturbations you could have, which are tiny, would be like coming from different streams. Actually, I have an interesting slide for the discussion session that might throw some light on that. But it's a good question. Thank you.
Enrique, these modes, MHD modes, 3 modes, do they form a complete basis? Can you say that any flow, MHD flow, can be represented as the sum of the 3? I think not. I think not.
Yeah.
This means that there can be other, well, parts of the flow which you do not capture by these 3 modes, which do something else, something different from what you were discussing.
Well, I think it's not exclusive, right? But one thing is that these are nonlinear MHD modes. So in fact, they're coupled. These are simple waves in the sense of Landau and Lipschitz. No? So that's why the Alfvén mode, in fact, can be linked to density fluctuations. But I would say that even if MHD turbulence is more than just the sum of these modes, for example, the action of these modes can help you understand what is going on.
No doubt.
Yeah, I wouldn't require all motions to be reducible to these modes.
But no, I was wondering very much about that. And to
Pardon?
me, I was wondering about this question. The answer isn't quite clear to me. Because obviously these are physically important things. Do they capture how much percent of the kinetic energy do they capture?
Yeah.
I think it's a question worth exploring. I will be doing with my simulations. It would be interesting to see how different codes compare and
Very good.
stuff like that. Thank you.
Interesting question.
So we'll have
But can't you just formulate?
Xiao next, and then Andre, and then the next speaker actually will be James Holland. So if James could come up.
If I understand your picture correctly, so according to the accumulation by the slow mode, you will have a very massive sheet-like structure formed. But how you explain the small-scale structure like coarse thin filaments according to this theory?
Can you repeat the question? How do I explain what?
Small-scale structures like coarse thin filaments in this picture.
Coarse in filaments in this picture? Oh, well, okay, that's a whole different story. Once the collapse has started, then what we have been claiming is that the clouds can form with a large number of Jeans masses, and then the collapse occurs in a roughly free-fall manner. They're magnetically supercritical, so they're collapsing freely. And when you have pressureless collapse, then the gravity amplifies anisotropy. So the collapse proceeds to form sheets and then filaments, and then from the filaments you get coarse. So that's the rest. That's the other half of the story that I didn't talk about it, and I'll be happy to discuss it.
So while we're setting up James, Andre, one last question for Enrique.
There's just a short comment. So you have 8 degrees of freedom, 8 variables in MHD, and you have exactly 8 modes. If you include an entropy mode, of course. So there is always a formal way to decompose. It's just that they're not always necessarily good waves. They have the right polarization, but they're not necessarily weakly interacting or anything. The base is complete. Yeah, the base is complete. We know that.